Okay, welcome to this lecture on network analysis, or in the context of social media, social network analysis. What we are trying to do in this class is that we try to analyze different social media platforms. Could be everything, could be Twitter, now X, Blue Sky, could be Twitch, and try to understand how people interact with each other in this network. So everything we're gonna talk about today is sort of coming from graph theory originally, from the mathematical concepts, where we want to represent something as a complex social structure and use mathematical models, in that case graphs, to represent the structures. This is extremely powerful, but let's directly jump into the topic. So let's see how this works out. Very good. So basically, first of all, the method we are mainly using is called social network analysis. In short, it's called SNA. You might hear this term or see this term quite often. And it is quite interesting because this is showing us how science interferes in so many different aspects. Also, the different disciplines of science would connect here. What do I mean with that? If you think of the potential of analyzing different social networks, this could be relevant for us as in computer science to understand better the social networks, social media networks we are designing. It could be like in general, like network from computer science perspective. How do we, like if you think of the internet and how we are all connected, the technical components. But if you think of other disciplines like social sciences, psychology, biology, so basically in how people would interact with each other, how animals would interact with each other in social structures. And all of this is using the same techniques basically, but it's interestingly sometimes using different wordings for the same terms or same concepts. So in general, social network analysis, the definition would be a strategy for investigating social structures through the use of network and graph theories. And we would usually call for instance, if you want to analyze a network full of people, so most likely the people would be, for instance, nodes. Some disciplines call them actors, directly people. Like it could be also topics, however. So we can apply it on all different sort of concepts, and the connections between the people describe, for instance, the relationship. This can be ties, edges, and we basically want to model and understand the world around us, to gather new information, to learn how people befriend each other, how they connect, how they influence each other. It's a very, very powerful concept. It started off with a concept called the 6 degrees of separation. 1967, this is quite some time ago, Stanley Milgram, who you might know from other experiments, the Milgram experiments, who was a psychologist at Yale and Harvard. But he was also known for another experiment called the small world experiment, or later this 6 degrees of separation concept. What does this mean? So 6 degrees of separation basically means that every one of us on the world sort of knows each other through 6 degrees of separation. So I might know someone who knows someone who knows someone who knows Barack Obama, for instance. This would be in that case like maybe 4 or 5 separations. We also call it sometimes the handshake principle. If I would try to understand how many handshakes am I away with Barack Obama, I would think, okay, who is the most probably politically known person I know? So I already shook hands with the Austrian president, for instance. He most likely shook hands with Obama at some point. So this would be then me to our president, the Austrian president, to Obama would be 2 degrees of separation. And already in 1967, this was way before we were all connected very, very easily with each other through the internet, there were already some experiments to understand better how well we are connected. What he did, let me quickly show if I have a graph on the next, yes, perfect. So basically what he did, the idea was he was sitting in Cambridge, close to Boston. You can see it here on the right side of the map. This is basically where he sent away different packages all around the states, to different people, to random people around the states, with the goal to send it to one specific person. I think it was a lawyer in Boston. And people would start. So here you can see there's a start in somewhere in Nebraska or Kansas. And this person thought, oh, I'm going to send it to someone who is geographically closer to this person. I send it to a friend in Iowa. The friend in Iowa thought, oh, Indiana is also so much closer. I'm going to send it to Indiana. The person in Indiana said, oh, I do have a friend who is also a lawyer who might know the other lawyer. He's in Tennessee, so I'm going to send this package to Tennessee. And most interestingly, so you can see here, we have to start to Iowa, then Indiana, then Tennessee, then Virginia, then New York, and then the finish. This is 6 degrees. And if we go back, they found that of all the different packages which were in the end received by the contact person, so some were with 5, some were with 7, they would build the average path length, and this was then 5.5. And this was the assumption that in average there's 6 degrees of separation between us. And this study was reproduced and continues to be reproduced, and we could see, because now with the internet it's a little bit easier, we don't need to send packages anymore, we can just see in a general network like Facebook or Twitter or Twitch or whatever, how far are we away to each other, basically, in this giant online network. In 2008 there was a study Microsoft showing that the average chain of contacts was on MSN back then 6.6. And now with Facebook and so on and so forth, I think it's now below 3. But however, what is quite interesting is that this was reproduced for different application scenarios. One of them, this is super famous, this is the Adosh number. The Adosh number, so Paul Adosh, you can see it in the small picture down here on the right, was a very famous mathematician. And he was known to write a lot of papers with different authors. So Paul Adosh himself, he has the Adosh number of 0. And someone who wrote a paper with him, directly with him, would have a Adosh number of 1. So this would be Alan Taylor, Jung, or Peter Hamburger. So they would have a Adosh number of 1. Altman would have a number of 2 because he wrote a paper with someone who wrote a paper with Adosh, and so on and so forth. And it's quite interesting. So sometimes you find CVs of scientists, mostly in mathematics, but also in computer science, who would even note what is their Adosh number. So I think pretty much every one of us in computer science or math we do know our Adosh number for weird reasons, and there's even tools to help you calculate this. And I'm not explaining the jokes on this slide, but the XKCD comic even made a whole comic series out of this. But there's also another one. So this is known in the computer science world, but there's also the Bacon number. This is the Adosh number. Okay, but the Bacon number, I don't have a slide for that. But it's very similar principle, but with actors. And Kevin Bacon is known to be in so many movies. And every time someone would have been in a specific scene with Kevin Bacon, they would have a Kevin Bacon number of 1. So you can also calculate of authors what is their Kevin Bacon number. At some point, I tried to introduce a game dev number. I don't know, Romero number, Carmack number, maybe the Pirker number. It was not that well received yet, though. Let's see how this will turn out. Anyway, so this is basically this idea to understand better how connected we are. There are, however, also very other application scenarios of social network analysis, and this goes way, way beyond back in time. So very early on already, Lada Damick was and is very known in this field, for instance, analyzed the presidential elections. So what you can see here in this graph are actually political blogs. And the nodes would be the blog websites, and the connections would be every time a website would link to another blog. And you can see here that sort of like, I mean, it's a little bit obvious, but it should be also make us a little bit critical that most of the time, different blogs from like belonging, for instance, to the Republican or the Democratic Party would only reference to blogs or quote and cite other blogs from the same party with the same interests. This is also quite interesting. This was a HP trying to understand how informal communication within the lab would work. So they did represent the email delivery at the HP labs. And what is quite interesting to see, it's very obvious that there are specific hubs, which are maybe project leads or group leads. But what you can see here, for instance, here you can see my mouse. Over here, there's very obvious a hub where one person is spreading the information to probably the team or like a large group of people. Why is this important to know? What if this person has a sick day and is not able to inform or send and spread the important information to their team? Or like more gravely also, if we are missing very central hubs where all of a sudden the information is not being forwarded. This is a little bit of a fun experience. I think this was all by Lada Damick, but also a very cool paper where they analyzed ingredients. So every time 2 ingredients were put together in a recipe, they would link together, and you can directly see here, this is like a little bit more, maybe the spicy side where you have garlic, peppers, black pepper, onion. Here you have the very sweet side and a lot of sugar, butter, egg, milk. And then in between, a lot of ingredients which are very heavily used by both, like salt, oil, water, lemon juice. And this is, if I would ask you, why is this relevant? Just think for yourself a little bit. What could this be used for? I mean, this sounds now fun. There's, by the way, a similar thing about cocktails. Of course, for instance, to understand better what could be recommendations, so like keyword recommendation systems for sweet recipes, or what other ingredients, which I don't have in my recipe yet, could be useful here. Or if I have a list of ingredients which are like with me at home, what other ingredients are often put together, what should I still buy? So this can be very useful for recommender systems, for instance. But also, of course, disease. During COVID, this is was such an important tool to understand better what sort of like contacts we should try to avoid, or what rules should be put in place to avoid spreading, in this case, COVID, but also in general specific disease. So what could be useful rules. So also like COVID regulations, or in general pandemic control, is very heavily based on mathematical models. And here, this is like one paper which describes romantic relationships in a US high school over an 18-month period. And what you can see is also like the dangers of potentially transmitted disease in such a network, because such a network all of a sudden becomes very large, even if you think you might be only in a small graph. So this is quite interesting to look at and to understand also for medical and health purpose. If I would be in class now, I would try to motivate you to discuss a little bit and think about for yourself what you think are interesting network analysis concepts. What are other interesting application cases? Where did you have experienced this being used, or what do you think it could be used for? So maybe if you want to, feel free to write this down, add this to the comments, or just do it for yourself at home now. There's also a fun game to play. This is called the Wiki game. I'm not sure. Like, should we play it now? No. I'm not spoiling this. You should play this, but this is actually pretty fun. So this is basically the idea. You start at the random Wikipedia page, like here. You start with Janet Jackson, and your goal is to somewhat reach the Wikipedia page college in as little steps as possible. And all you're allowed to do is to click on links within the starting page or the next page. So with Janet Jackson, you want to come to somehow to the path to college. It's called the wikigame.com. I really recommend you playing this. It's a very, very fun and interesting game. And this basically uses the same principle. So in this case, you're trying to minimize the path. And they build a game around this graph concept. So to summarize a little bit, the application of social network analysis can be super broad. We can understand the way how we as a group work, as a world work, how communication works, how collaboration works, how information sharing works, how friendships are built, how communities are built, what is a trust network, how do we share information, how diseases are transmitted, about health protection, about marketing, of course, but maybe also building games around that. So there's a whole range of application fields in so many different domains. Like, I could not think of any domain which I would not find a really interesting case for using these techniques. What tools do I recommend? If you're new to SNA, social network analysis, there's one really neat tool which is called Gephi. Gephi.org, where you basically load your graph structure. So you at some point you want to have built this connection structure. Most of the time we use a matrix format for that. Gephi is a very, very cool tool where they have already some networks you can like play around with, and then gives you different ways to analyze the network but also visualize the network, because in the end, like, everything I just showed you was built on visualizations. So visualizations are for us so important to understand how this works and how we can use it, and not so much in the mathematical numbers, the models, the numbers, and so on and so forth behind, because sometimes the visuals are so much easier for us to understand and interpret the data, especially when it comes to graphs. Again, even though everything is built pretty much in the realm of, for instance, matrix calculations. SnapPy is also a very interesting framework. There are different R packages which are super useful, and you can also do your own visualizations like we did in many other classes as a recommendations. For instance, D3 is quite a cool tool to give you different visualization techniques for that. For instance, here you have an overview of all the characters. There's another really cool overview of all the Game of Thrones characters, for instance, and how they are connected, what are the intrigues, and not showing this because of spoilers. I mean, what are other unusual applications? So for instance, predicting economic development using product-based networks, which countries produce which products, learning about cooking from ingredient and flavor networks, we looked at that, or the social network of dolphins. So there are so many different application cases where this can be useful. This is just a little bit also like the written summary of what we just said. Mathematical network models allow for better understanding of phenomena observed in real-world networks by providing concrete mathematical explanations. And they allow for controlled experiments in synthetic networks when real-world networks are not available. This is also something which is quite interesting with the tools I showed you before. You can run different networks. So for instance, what would happen if this network is growing like very fast, if there is specific information or like disease being spread at specific points, where would you need to, just to give you an example, where should you cut a network or try to cut a network to avoid spreading, or where would you start spreading something, for instance, information about something, to have it spread as fast as possible. When we look at a network, again, this is this giant graph. There are different things we might want to understand. Typical questions we would ask ourselves: who are important central figures, influential individuals in network? Again, for instance, if I want to spread information, who should I give this piece of information to make it as fast spread as possible? What are interaction patterns among common friends, for instance? What are like-minded users? How can we find similar individuals? How to represent various social networks? What are weak or strong ties in the network? And now let's dive a little bit into the basics, how this actually works. I already mentioned before, so those points and lines, how we can describe them in the easiest way, they do have different names depending on what field they're coming from. So they should not be like complicating things. It just should explain that sometimes in different fields we're talking about the exactly same things or methods without knowing it, because historically they have been evolve different terms describing the exact same concept. And this is a very good example for that. So in math, we typically would call it vertex, and then the lines would be the edges or the arcs. In computer science, we typically say nodes and links. So this is like my node and this is the link in between. In physics, this is sides and bonds. In sociology, this would be actors and ties or relations. But in general, so we mostly in our class, we will stick to vertex and edge or nodes and links. And what you can see here, this is like a very normal graph, but we have different forms of graph. So for instance, this is the directed graph. If you think of a platform like Twitter, or now we call it X, you could follow someone, but this person does not necessarily need to follow you back. So this would mean vertex 2 is following vertex 1, but vertex 1 is not following back. Vertex 2 and vertex 3, however, they are following each other. And this is like called a directed graph if you have information and you want to use it about directions. So for instance, on Facebook, I mean, now you can also follow people on Facebook, but back then it was you are connected or you're not connected, and you can see each other's profiles. The undirected graph would be this one, where you don't have any information, or you don't maybe need the information about the direction of the graph. Then we have the degree. So here, this is already coming some representations how we do the actual math. So we would use a matrix defining the graph. So for instance, if we1 and we2 are connected, we will make sure that we1 and we2 have a 1. This line is either, depending on what representation you use, it should be 0. Sometimes you find all ones here. So v1 and v1 are usually not connected. It's like the same, so you would have like a line of zeros. Some representations use a line of ones here. But 1 and 2 are connected, so you put a 1 here, you put a 1 here, because this one is a graph which is not directed. So it should be a symmetrical matrix. V3 and V2 are connected, so V3 and V2, there's a 1, V2, V3 and V2, and there's also 1. And so on and so forth. This is how you would describe it. The term degree would describe how many connections has a graph. So this is the degree. The point So in this graph, we have like one vertex which has the highest degree. This would be V4 because 1, 2, 3 connections are going in or out in V1, V4. If I go back to this one, I can differ between degree in, how many connections are coming in, and the degree out, how many connections are going out. So this one would be a degree of 2, a degree in for 2. This would be degree in and out, this one. Degree in would be 1, the one from V3. Out would be 2, because I'm connecting to V1 and I'm connecting to V3. So this is like how we describe the degrees. Often degree is like one of our most important measures for things like, we talked about it before, influence, for instance, and identifying sort of like the position and the value of this vertex in the graph. Some important wordings here would be, for instance, degree centrality. This would describe a high degree. How central is my node in the context of the whole graph? So this one has, for instance, a very high degree, so it has a very high centrality. Look at this one. Which node has the most edges? You can identify, here's one, for instance, which are with a very high degree. This one most probably down here. So this is like something which you can also try out at home. Try to find here, like what is the degree of the single vertices. This degree centrality we see pretty much every day, because, for instance, many sites are visited less than 1,000 times a month, whereas a few are visited more than 1 million times daily. So this describes a little bit this high degree in the centrality. Most social users are active on a few sites, whereas few individuals are active on hundreds of sites. And there are a few social media users which have a lot of people, for instance, following them. I think of Instagram, whereas a lot of people following many other users. This next term we're going to talk about is the giant component. There's sometimes a little bit misunderstanding. What we're not talking about is a fully connected graph. So when we look at, like for instance, this graph earlier, all of this, even though like there are like plenty small graphs as well, we still call all of this our network we want to analyze. All of them together. So even though they are not necessarily connected, this is like the whole structure we want to analyze, and not necessarily only one specific fully connected graph in there. We are talking about this full structure. And this is now important, because if you want to really focus on one specific network which is like fully connected, one fully connected graph, this is what we call the giant component. If the largest component of a graph would encompass a significant fraction. So in this case, it's very clear. Like there's one very obvious fully connected graph within this full structure, which is the majority. And then we have some like subgraphs which are relatively tiny compared to that. This does not mean necessarily that there is always a giant component. Sometimes we have several graphs which have a similar size but might not be connected to each other. Speaking of connected to each other, this is where betweenness is super relevant. Betweenness, sometimes we misuse the wording of important actors in a network, because importance, we sometimes think of, oh wow, this person has a lot of Instagram followers, for instance, so the very central, very high degree. This is not what we mean by important. Important in terms of how important is this specific vertex for the rest of the graph. And if you think of a graph like this, there might be some nodes which have almost no connections at all, very low degree, but are super important because they are connecting different graphs. So just think about this being a giant graph, this left side, and then think of having a second graph on the right side, which is also huge. And then you have, like, for instance, these actors in between who only have a degree of 2 maybe. This is called the betweener. These are called the bridges, forgive me, here. This is called the bridges because they are connecting those graphs and are an important link. So in between us means basically how well is this one connecting other graphs to each other or other nodes to each other. Closeness. This would be describing, looking at two nodes and how close are they to each other. This can help us also describing the complexity of a network. Is the network in general like very well connected to each other, or are there sometimes very long paths which we need to walk through in order to connect two nodes to each other? And here are, like, for instance, the average path length. This would be describe what Milgram actually did. So if we look at all the different nodes in the graph and look what is the shortest distance between connecting them, and then what is the average length to have them all connected. And this is what I referred to earlier. So this is again a little bit older graphics, but showing you that in the general website they did experiments. Again, this changed by now, but back then it was 16.12 to have all websites connected, 4.7 to have all Facebook users connected, and so on and so forth. So we do have different ways to describe the graph. Another one is the weight, the direction we already had, and the intensity of the relationship. And if you think for yourself, think of Instagram. Facebook might be not so known anymore. How could you measure the intensity of a relationship between two users? How could you measure this? If two users are connected and you would have maybe the information you can just see, versus you have information as a social media platform which other users don't see from the outside. How could you measure the intensity of the relationship? I'll give you a few seconds to think about this yourself, or you can also pause now and write down. To give you some answers, for Instagram, for instance, it's very typical if they tend to like each other's images more often compared to other users, if they would comment on each other's profile more often than other users, if they maybe tag together in specific pictures, if there any sort of interaction which is visible from the outside. Versus what you could also do if you're like social media platform owner, you can also, of course, count the numbers of messages which are being sent to each other. And this is called the weight. So what we tend to do, so for instance, if we know, okay, we do have a direction maybe of the network, but we can also say we want to use a weighted network. So, and add specific weights in the calculation. So for instance, this one is writing this person a lot and send 3 messages. This would be a weighted direction of 3, versus this one is following this person even like a little bit less, just send like 1 message in return. So this would be a weighted direction of 1. And this one in this direction is a 2, and in this direction is a 1, for instance. This is how you can add weights. So you can define, those persons are not only connected on Instagram, for instance, they're following each other, but even though like 2 people are connected to a specific person, one might be more connected to this person because this person liked 20 of the Instagram posts. This is how this could be working. So this is all about identifying a little bit this structure within the network. Everything, it does not necessarily everything needs to be connected. What we can see here, this is what I talked about earlier, there might be even subgroups which are super different from the main graph, but could be especially because of that super interesting for our analysis. We also might be specifically interested in, so this could be either our outliers which we don't want to analyze, or it might be even like part of our research question. How can we integrate them into the network? Because obviously they're not getting the information and so on and so forth. This would be also like if you would be now in class, some questions again which you can ask yourself. Again, to give you the idea of different application fields. Which countries, for instance, have high in degree? So import petroleum and petroleum products from many others. If you think of those countries, Saudi Arabia, Japan, Iraq, USA, and Venezuela, which countries have high in degree import petroleum and petroleum products, which are receiving a lot of others? And this is how this looks like. So you can see this is a weighted graph and it's a directed graph. So we have very strong incoming from Venezuela to the US, Saudi Arabia to the US, Japan from Saudi Arabia, and so on and so forth. So you can see there's a few countries which are giving a lot of, exporting a lot, and a few who are importing a lot. So this is like, for instance, to give you another use case. And let's change this question. Which country has low out degree but exports a significant quantity of petroleum products? Low out degree but exports a significant quantity of petroleum products. And here you can see there's again pretty much the same graph. And I'll leave this up to you to solve this one. And again, feel free to write this or write it in the comments if you do know the answer. Good. So social networks. Back to social structures here. When we think about again social networks, whether it's Instagram or Twitch or X or Facebook, there are different questions we tend to ask. Who are central figures? Again, importance is such a difficult word sometimes in our head. So we call it central figures, influential individuals in the network. What interactions patterns are common among friends? Who are the like-minded users? How can we find similar individuals? Why is this important? You can also think of a video game. Also in a video game, we can use the same methods. Maybe want to recommend good groups to which are able to play with each other because they have a similar play style, they have similar play times, and maybe like also the setup of the figures would work well together. And this would be again a little bit of a brainstorming question. How important is a node within the network? Which nodes are important and could be important? And real world examples. I did spoiler already some of those on the earlier slides. So let's look a little bit at different factors. So we are back to centrality. How important is a network within, important is a node within the network? And here is already the description how you can calculate this. There are like the links are on all the slides where you can find more information about those topics. So the degree centrality would describe people with many connections. So in this one, very obviously, V1. And you would basically describe this by describing the degree of the of this point. So this one having a degree of 1, 2, 3, 4, 5, 6, 7, 8, and has obviously a higher degree compared to V2, who has only a degree of 1. You can describe the prominence would be the in degree, or the gregariousness, which would be the out degree. So some people have a lot of followers, some people are following a lot of people, maybe being interested in a lot of topics. So you can hear them describe also or make a difference when the graph is directed and you have information about the directions. Important is that you normalize degree centrality. So for instance, if you want to compare Facebook centrality with Twitter, you of course want to normalize it. So normalization usually works very nicely in the most simple way when you describe it by the max possible numbers, but you can also describe it by the max degree or the degree sum. The next one is the eigenvector centrality. So there are different forms of centrality. So this one was called degree centrality. This one is called the eigenvector centrality. This is, by the way, also how the original Google algorithm used to work, called PageRank. This would be if it's nice if you have a lot of connections, but it's even nicer if the connections you have also have a lot of connections, so that your friends are important or also very central, basically. This is a stronger signal than having just a lot of followers. Just think of an account who might have maybe bought a lot of bots. So for instance, they have 100,000 followers, but all of the 100,000 followers only have one other follower or none at all. So this is basically then if they would share your tweet or whatever, it's pretty useless because it will not spread any further. However, if you might only have one follower, but this one follower has more than 1 million, because this might be, again, maybe that's Barack Obama, and has millions of followers who might also have like millions of followers. If this person, even though you have only this one follower, if this person would spread and share your tweet or whatever, this is way more powerful than 100,000 bots with 0 followers sharing your information. So this is quite interesting, and this is the main principle how an algorithm like PageRank would work. Then there are, again, like based on this eigenvector centrality, this is how it's called, where you assign relatively scores to all nodes based on the assumption that high scoring nodes contribute more to the score. There are specific terms for that. So the cuts centrality, for instance, because there's a problem with the standard eigenvector centrality with directed graphs. The centrality only passes on for outgoing edges. And in the cut centrality, you have a bias term. And this, however, has another problem. Once a node becomes an authority, which means has a very high centrality, it tends to pass all its centrality along all of its outlinks. But not everyone knows by a well-known person is well-known, right? So what you want to do, and this is in the end how PageRank works. PageRank is pretty known, that you would divide the value of past centrality by the number of outgoing links, so the out degree from that node. This is how this looks like in the end. The third term is called betweener centrality. This refers to what I mentioned earlier. There are also very important nodes connecting other nodes, and this would compute how important are nodes in connecting other nodes. So this would, here you would compute the shortest path between other nodes that passed through this specific node. And then you can measure how central this specific node would be in connecting any other pairs. Dijkstra, I suppose you all still know in that context. But yeah, so this is basically this betweeners as a centrality measure of vertex within a graph. Betweener centrality quantifies the number of times a node acts as a bridge along the shortest path between two other nodes. Again, think about those big graphs being connected by a few nodes who only have, a couple of connections at all, but they are also super important, and this is how you can calculate this. So this one, look at this, find a node that has a high betweeners and a very low degree. Give you a second. And here comes the answer. So obviously G has only a degree of 2, H only has a degree of 2, but they have a very high betweeners because they're connecting those two. And the last one is the closeness centrality. And this would be sort of being in the middle of things. The more central nodes there are, the more quickly you can reach other nodes. And these nodes have a very small average shortest path. And you also want to normalize. In this case, you just divide by the maximum. In a connected graph, the normalized closeness centrality, or closeness, how it's also called, of a node is the average length of the shortest path between a node and all the other nodes in the graph. Thus, the more central a node is, the closer it is to all the other nodes. So we're really looking one which is if someone is trying to spread information, we want to have like a very short, for instance, sending emails. This should be just like a few sent out emails, basically trying to reach as fast like the whole graph. This is like when closeness centrality becomes very handy. Which node here has a very high degree but low closeness, for instance? So, I mean, this one has a very high degree, but is pretty much in the middle. This has a high degree, but is not so central, for instance. Because you have a very, very, the time to reach B would be very high. And this is now a little bit of an example. You have now A, B, C, D. And now it's up to you that you decide, looking at these numbers, which one visualizes the closeness centrality, which one betweenness centrality, which one the eigenvector centrality, which one the degree centrality. Again, maybe pause here now to make the assignment yourself. And I'm gonna reveal the answers now. So A is exactly the betweenness centrality. So everything which does have a little bit of a color here is relatively lovely connecting the different graphs in between. B would be obviously the closeness centrality. So we can see here everything which is pretty much here in the center, being able to reach all the other nodes relatively fast. They have a higher closeness values, whereas these ones are to have not so high closeness values. C is the eigenvector centrality. So you have a lot of nodes which tend to also have a lot of connections themselves. And then D would be the degree centrality. So those nodes don't necessarily need to be close to each other. We can see, okay, there is one which has a very high degree. There is one which obviously has a very high degree. And there could be also ones at the border places. Good, well done, hopefully. Then let's move on. How is this useful? I think in the introduction we covered already a lot of cases here. Simulations, hospital patient transfers. So if a patient transferred, the hospitals could collaborate to find hubs of key disease transfer point and try to understand what, like, if we run some simulations, what would be here the best places to allocate money to allocate the transfer the patients to, and so forth. There are different strategies, for instance, for a question like this. And again, I think with a tool like Gephi, you can actually run some of those simulations. But for instance, you can try random techniques, which pretty much has no effect. Using degree would be a bit effective. Betweenness would be more effective. Greedy would be most effective. Or eigenvector would be also pretty much effective. This is the simulation point to that. Good. What is also quite fun is to look at the community analysis. So within the graph, you can not only look at the different like single points of interest or actors, persons, whatever, but you can also describe different groups, communities within this network. So we can detect them, we can try to see how they evolve, and we can evaluate them. When we think of social communities, there are different forms of communities. So for instance, there are real-world communities, body of individuals with common economic, social, or political interests. Virtual communities would be like-minded users on social media who form a link and start interacting with each other. So this could be, for instance, people sharing same interest. They could be groups which are very obvious. So for instance, in Facebook, we all belong to the same, boxing club, and we all like the same page or are part of the same group. Or we do share common interests, and we can still be somehow grouped together through those patterns. Explicit versus implicit communities, that's what we call it. So two explicit communities would be, for instance, community members understand that they are part of this group, and non-members understand who the community members are. So if you're part of a specific group, boxing group on Facebook, everyone from the outside sees, okay, everyone who is part of this group belongs probably to this boxing association. And then there are implicit communities. Members might interact with each other in a form of an unacknowledged community. What could be, for instance, here quite interesting, coming from this games realm and analyzing a lot of game spaces, I could still, if you're playing World of Warcraft, I could try to understand, oh wow, you're part of the same guild, so this is very explicit. Oh, however, you might be still connected, a group of all of you, because you're sharing the same geographical in-game place, the same coordinates every time you play. So obviously you're sort of playing together. This was the first part. We directly jump into the next part. But for the first part, I really want to recommend these readings, which I find highly interesting. So social media mining, into an introduction. Then here, the Coursera course by Lada Adamic. I hope this one is still up. This was super interesting in the book Sentiment Analysis and Opinion Mining. Good.